Okay, hello everybody. Good morning, all of you. And today's quote: failure, failure will never overtake me if my determination to succeed is strong enough. Okay, so that is more important. So the determination to succeed. So if that is there, it is like your immune system. If you feel that you will not get anything, you will not get it. So, but okay, you have to take enough care. But if your immune system is strong, nothing can affect you. In the same way, if your determination is strong to succeed, so nothing can make you failure. And okay, today is the birthday of Wilhelm Maybach. I don't know whether you heard his name. If you are Icenians, if you study well, you will come across this name. He has come with a carburetor. Okay. So, German engineer and engine designer who invented the spray carburetor and was the chief designer of the first Mercedes automobiles. At age 26, he began designing cars with the Gottlieb Daimler and the Nicholas Otto. So this Otto, and with whom he developed the four-stroke engine cycle. In April 1882, Maybach joined Gottlieb Daimler in a partnership to produce lightweight, high-speed petrol engines suitable for vehicles. And he invented the float-feed carburetor, in which fuel was vaporized by passing it through a jet as a fine spray and mixed with air to produce a combustible mixture for the engine. He designed the first Mercedes car for Daimler in 1901, but retired in 1907 to design and manufacture engines for Zeppelin airships. His son Karl Maybach followed him in producing luxury automobiles. So he's a very good contributor in the automobile industry. And okay, today we will have the hyperbolic solvers. But before going to hyperbolic solvers, we will see what we have done in the last class and a little bit extension to the last class also. We will do. Okay, last class we have talked about three topics. One is consistency, and another is stability, another is linearization. So we have seen what is consistency. So when we have written partial differential equation as finite difference equation, and if I substitute back these Taylor series expansions into that, and if you see under what condition it becomes the original partial differential equation. So usually it will be delta t tends to 0 or delta x whole square tend to 0, like that will be there. And sometimes there will be some additional particular restriction will be there, as we have seen in Dufort-Frankel scheme, where delta t by delta x whole square also should tend to 0. So like that. So the order of accuracy also we get from that, the consistency requirement. So we have done that consistency check on FTCS scheme of parabolic equation, and also consistency check on Dufort-Frankel scheme of parabolic equation. And then we have discussed about what is the need for linearization. So whenever I have a nonlinear term, and if I convert it into algebraic equations, I am not going to have linear algebraic set of equations, but nonlinear algebraic equations we get, which cannot be solved by normal regular Gauss-Seidel, Gauss elimination like things. So there should be other iterative methods. We have to use advanced methods. So instead of that, if I have some method of linearizing the nonlinear terms, like there are three methods we have discussed. One is the lagging method. So one value, we will take the old value or previous value, like that. That is the previous point value, so that the product will not be a nonlinear term. Similarly, iterative method. So we assume some value and go on updating it till you get the convergence. So that value is to be used. And the other method we have seen, Newton's iterative linearization method. So if I have two terms like a and b, which are both are function of dependent variables. So a k plus 1, b k plus 1, both are new terms. If I have the nonlinear term like that, so we have seen how to linearize it, like a k b k plus 1 plus b k a k plus 1 minus a k b k, like that event. So k are the old values, k plus 1 is the new value. So ak bk plus 1 is linear, and bk ak plus 1 also is linear. So that is the way we approximate. And because there we are doing a little bit of approximation by eliminating delta a, delta b, which we get. So we neglect the term, assuming it to be small. So that assumption makes it linear. Then we talked about what is stability. So whenever you use a computer, So we are bound to have some round of error at every point. So if I have a round of error at a particular point, and how it is changing as iterations progress. So if the ratio of the round of error are the present and previous ones, if the modulus of that is less than or equal to 1, then because gradually it is going to decrease and it is going to be stable. Okay, that is stability. And in von Neumann method, so what we have seen that is exact solution of finite difference equation if you take as D and numerical solution as N, because D has to satisfy that equation and N also has to satisfy equation, and D minus N, which is the round of error, and that round of error also has to satisfy the equation. Okay, so we have to just replace the dependent variable with epsilon, and the expression for epsilon is given by von Neumann as assuming that the error, the round of error, changes with time and space, and exponentially in time and trigonometrically in space. So it is given as a term e power at e power ikmx, where km is the wave number. So that is the way if you substitute. So here the amplification factor, that is the error at n plus 1th iteration by error at nth iteration, which becomes e power a delta t, which is amplification factor, that modulus of e power a delta t should be less than or equal to 1. So we have to check for every scheme what is going to have for that e power a delta t, whether it is always less than or equal to 1 for any condition, then it is unconditionally stable. If it is always greater than 1, then it is unconditionally unstable. If on some condition it is going to be less than or equal to 1, that condition makes it conditionally stable. Okay, so that condition for stability we have to find out, and that we have to done for FTCS scheme and BTCS scheme. And for the FTCS scheme, we found that it is conditionally stable, and the diffusion number, which is defined as alpha delta t by delta x whole square, that must be less than or equal to 1 to make the amplification factor decreasing or less than or equal to 1. D less than or equal to half. Okay, that is the condition for stability. And when you take the BTCS scheme, we have seen that it is always less than or equal to 1. I need not have any condition to satisfy the stability. So it is unconditionally stable. Okay, so these are the things we have checked in the last class. So there are further points on von Neumann stability analysis. We make it. So one is, so these are important. We have to remember them. And these are applied to linear equations only. Okay, it is proved that that will work for linear equations only. And the other one is because sometimes boundary conditions also derivatives will be there. And I'm using some scheme for that also. But we are not checking what is the effect of that on the stability of the scheme. So the influence of the boundary conditions on the stability of solution is not included. And for a scalar PDE, which is approximated by a two-level of the finite difference equation, the mathematical requirement is imposed on the amplification factor as follows. So when you have the amplification factor, we have seen that if mod g less than or equal to 1, it is stable if g is real. But sometimes because e power ikmx is there, and in the previous schemes, we got e power I theta plus e power I minus theta, e power minus I theta, which become 2 cos theta. But later we are going to do this for hyperbolic equations, where I am going to have a complex number for amplification factor. So if it is a complex one, then I have to check mod g square or g bar should be less than or equal to 1. G bar means it is complex conjugate of g. If g is complex, g bar should be less than or equal to 1. So this is the one actually we are going to do when you check for hyperbolic solutions. And then if I have if G can be matrix, okay, sometimes if I have simultaneous equations, then I will have a matrix. So if it is a matrix, I have to find eigenvalues of the matrix. And if lambda mod lambda less than or equal to 1, that is lambda means eigenvalue. If lambda is complex, then mod lambda square is less than or equal to 1. And the method can be easily extended to multi-dimensional problems, as we have shown that for a two-dimensional problem, dx plus dy should be less than or equal to half. That can be proved. In the same way, if it is 3D also, dx plus dy plus dz should be less than or equal to half, which we have taken. And so d should be less than or equal to 1/6, like that we have. So it can be extended to multi-dimensional problems. And the procedure can be used for stability analysis of a system of linear PDEs. That's what here also we have discussed. The requirement, okay, when you have multiple eigenvalues, and then I have to check on the largest eigenvalue of the amplification matrix. I have amplification matrix, and I find the eigenvalues. So you take the largest value, and that value should be less than or equal to 1. Okay, so these are the conditions or limitations for von Neumann. And another thing, okay, there are benchmark values usually. Okay, so you can remember if it is a parabolic equation like unsteady heat conduction equation like that, the diffusion number, which is defined as alpha delta T by delta x whole square, should be less than or equal to half. So this is a general one for all explicit methods. So even without checking also, if you take care of that, okay, because stability analysis sometimes may be difficult to do it, and you maybe mathematically may not be strong. So you can just blindly use this particular condition. If you satisfy this, mostly you will not have any problem. And if it is hyperbolic equation, then there is what is called as coherent number. Similar to diffusion number, I will have coherent number. If you remember, okay, this anyhow we are going to do. So when you take the hyperbolic equation, we have first order wave equation as ut is equal plus aux is equal to 0. So where a is Swan equivalent. Okay, a second order wave equation. This we have discussed these things. Utt is equal to a square uxx. Okay, so these are the wave equations. And here, so if you take the first order wave equation, here I am going to get by delta t, here I am going to get by delta x. So there will be a number called a delta t by delta x, similar to diffusion number, where I got alpha delta t by delta x whole square. And this is called as C, which is coherent number. Okay, so we are going to have, for explicit schemes, just similar to d less than or equal to half, I'm going to have c less than or equal to 1 as condition for stability for explicit schemes. Usually, right? So these are general benchmarks. And suppose I have an equation which is called as Berger's equation. Berger's equation, where I have like ut plus aux. I will have the convection term, and also is equal to like this. Okay, so this is kinematic viscosity. So if I have diffusion term and also the convection term, okay, then I will have, okay, here c is equal to a delta t by delta x, should be less than or equal to 1, and d equal to alpha or nu, both are similar because they are diffusivities. And when both are existing, there will be one more condition is given by REC is less than or equal to 2 by c. REC is not regional engineering college. So REC is called as cell Reynolds number. Okay, why it is called like this is defined as So cell Reynolds number is velocity into distance, right? A delta x by diffusivity. Like we will have u d by nu, right? Reynolds number. Or rho vd by mu, rho ud by mu. Both are same, right? So it will have some velocity into some distance and by nu. So here a delta x by nu I will get. This is, that's why it is called as cell Reynolds based on the size of cell delta x. So we got the Reynolds number, and C is current number only. So these are the three conditions to be satisfied. Anyhow, if two are satisfied, the third also will be automatically satisfied. That we will show in when you solve the Burger's equation, Burger solver.
Sir,
Yes.
Burger's equation is different from momentum equation because is it different? Like apart from the lack of pressure gradient term and body force.
Okay, this is actually not Burger's equation. I can say this is linear Burger's equation. Actually, this will be U.
Yes.
That is non-linear Burger's equation.
So only at a special case, U is equal to A, right?
Yeah.
Okay.
So these are the three conditions: current number C less than or equal to 1, diffusion number D less than or equal to half, and cell Reynolds number REC less than or equal to 2 by C. And for implicit formulation, mostly unconditionally stable. Okay, so these are the general things. If you remember, then whatever scheme you take, just you have to be careful whether these conditions for stability are satisfied or not when you are using explicit scheme. Okay. Okay, for multidimensional problems with equal grid sizes in all spatial directions, the stated benchmark values are usually adjusted by dividing them by the number of spatial dimensions. So if it is 2D, it will be C less than or equal to 1 by 2. This is D less than or equal to 1 by 4. If it is 3D, C less than or equal to 1 by 3 and D less than or equal to 1 by 6. Okay, so into the number of dimensions will come in the denominator because assuming that all delta x, delta y, delta z are same. Okay, so that is the way it will be extended. Okay, these are the general remarks which we have to remember. Okay, then we come to what is called as hyperbolic solver.
Sir, that current number less than equal to 1 is only for one dimension, right? But is it in the case of finite difference and finite volume also, sir?
Yeah, you need anything, whether it is finite difference or finite volume or finite element. We have to be careful about it.
If you are using 2 dimension, you have to use half. Okay.
Yeah, that's it.
I have used 1 till. Okay.
Yeah. Okay, so this is the model equation which we take, which is first order wave equation, and assuming A greater than or equal to 0, A positive. And as I told, this can be in general. You can take linear, inviscid, Burger's equation. Okay, so inviscid, so right hand side is not there, and linear, so U becomes so general Burger's equation, as I told, ut plus ux is equal to nu uxx. This is general Burger's equation. So now this is not there, and u becomes A. Okay. And so here, when I have this equation, again, if you want to solve, various schemes are used. Okay, the first, it is by Euler. Okay, there are some people who always put the finger in everywhere, right? And many times they are successful, but sometimes they may be unsuccessful, but they will try again one more like that. So when Euler came, so he came with a simple scheme, which is forward time, forward space. So if I take this at I and n, because it is explicit, okay. If it is implicit, I have to take it n plus 1. Okay, forward time means, you tell me, what will I get?
ui n plus 1 minus uin by delta t.
Is equal to minus a.
First order, first derivative, right? So ui plus 1 n
1 n, yeah,
minus ui n by delta x.
delta. Okay, so this is the scheme. So if you see the order of accuracy is in time, it is first order because one-sided difference, and in space also first order only, first order in time and space. But condition for stability, if you take, so it is unconditionally unstable. It is found to be unconditionally unstable. That is, the amplification factor is always greater than or equal to 1. So it will not work at all. So he found that it will not work. And so naturally, these are people of perseverance, and they will try another one. Okay. So because the FTCS has worked in parabolic schemes, so he has tried for that. So again, either only, and he came with FTCS explicit scheme. Minus AUX at I and N. So forward time, same thing on the right side, the left side, UAN plus 1 minus UAN by delta T is equal to minus A. Now here central difference for UX. So what will I get?
ui plus 1 n
UI plus 1 N
minus
minus
ui minus 1
N by
2 delta x.
2 delta X. Okay, like this. So if you take order of accuracy, it is first order in time, but because it is central difference in space, it is second order in space. Okay, when you check for stability, so it is unfortunate that this is also unconditionally unstable. Okay, so physically later people understood why it has happened like that, because A is greater than or equal to 0. The information is moving this way. Okay, so if I take I plus 1, I plus 2, I minus 1, I minus 2 like this, and if the information is going this way, right? So if I am discretizing at this point, I have to use the value which is behind it, but not the point after it, because I plus 1 will not affect I. So if you take the weightage of the next point will not affect it at all. There is no point in taking or using that point which is after that, because the information is coming from left to right. Left point will influence, but not the right point. Am I clear about the logic?
Yes, sir.
Yes, sir.
But is it always a, sir? That constant, it doesn't have to be sonic velocity, right?
Yeah.
In that case,
Here it is sonic velocity.
okay.
It is wave equation, right?
Okay,
So
okay.
we are not taking the momentum equation like that. It is wave equation. Later, we can extend this to the nonlinear equation, UUX.
Okay, sir, okay.
Okay. So then the third scheme came. That is forward time.
Backward space.
This is also called as windward differencing or upwind difference. So upwinding is a very popular name. Okay, so this is first order upwind scheme, because backward space, if I use only one point behind it, it is first order accuracy. So forward time, backward space. Again, if I take ut is equal to minus AUX at I and n. So again, forward time is ui n plus 1 minus ui n by delta t is equal to minus a. Now, the backward difference, how will you get?
UIN minus UI minus 1n by delta x.
By delta x. Okay, so here, order of accuracy, first order in time, and second order, first order in space, both. And stability, okay, this is conditionally stable. So as I told, the condition for stability is equal to C, which is A delta T by delta X, should be less than or equal to 1. So if you do the one Newman stability check, you will get C less than or equal to 1 as the condition for stability. Okay, so this is about, and this is very successful. And because this is first order accuracy, so you can go for second order accuracy. Later we will talk about that. Actually, there is what is called as quick scheme. Okay, later we will talk about this. So this is quadratic upwind implicit. Okay, this is implicit, but here it is explicit only. Implicit convection kinetic. That is for the convection term, when you have UUX, it is actually used for nonlinear scheme. When you use implicit scheme, if you use second order differencing for convection term, this is called as quick scheme, quadratic upwind implicit convection kinetic. Okay, so okay, that we will discuss later. Okay, this has worked, and because it is first order in time and space, again people are not happy because I wanted to have better. Once it works, as long as it doesn't work, I want it to be stable. But once it is stable, then I will try to have a better scheme. Okay, and so like Dufort Frankel and all, there is one person called Lax. So he has seen forward time central space, which is second order in space. Okay, so he tried to modify it. So he modified FTCS. Again, this is also explicit only. Okay, what is that he has done? Again, ut equal to minus AUX at IN. Okay, ui n plus 1 minus ui n by delta t minus a ui plus 1n minus ui minus 1n by delta x. Okay, this is FTCS. So what is the modification he has done is, he had taken uin and he has taken it to be average of its neighboring points, not previous old values like that, which is taken by Dufort Frankel. And he has taken, because that is 3 time level scheme, he doesn't want to go for that because it is a not self-starter and all those problems are there. So what he has done is, he has taken it as the average of ui plus 1n plus ui minus 1n by delta x. Like this he has taken. And so I will get uin plus 1.
Sir, it should be delta 2, right? Not delta x.
2 delta x, right. Thank you.
I mean, not 2 delta x. It should be only 2 because dimensionality will. Both
Yeah,
are
it is 2 only. I didn't write
you wrote delta x.
delta x. Okay. It comes like this. Thank you. And so this will become, this is equal to half into ui plus 1n plus ui minus 1n minus a delta t by delta x, that is c, into ui plus 1n minus ui minus 1n. Yeah. That's right. So we will get like this. So this again, if you take order of accuracy, delta t and delta x whole square. And if you take a stability, okay, he is lucky that it is conditionally stable. And stability condition is c less than or equal to 1. Okay, this c less than or equal to 1, this is actually called as CFL condition. Okay, given by three scientists. So C is Courant and F is Fredericks and L is Lewis. Okay, with respect to respect these, honor these people, they have called this current number less than or equal to 1 as CFL condition. A CFL condition is to be satisfied like that. Okay, and still people are not happy. They will try. They wanted to try it further, and so why not try CTCS scheme? That is central time, central space. Okay. Okay. So now central time means UI n plus 1. What will I get?
Minus ui n minus 1
Yeah.
by 2 delta t.
2 delta t. Thank you. Minus A UI plus 1n minus UI minus 1n by delta x. Okay, this is the way I get. So that the order of accuracy is second order in time and second order in space, and stability is found to be again conditionally stable as c less than or equal to 1. Okay, so then if it is good, second order in time and space, why to go for lax scheme and upwinding scheme? What is the problem with this?
We are ignoring the latest time one.
Not that. Actually, if you just remember the problems with the Buford-Frankel.
Starting
Storage
problem.
problems.
It's
Storage
not
problems, starting problem.
not self-start. This is 3-time level scheme and not a self-starter. And starter affects the accuracy. There, it depends on that. And also, if you see the values that depend on, somebody is telling about this, I think. Okay, if I take I plus 1, I minus 1, n minus 1, n plus 1. So we are calculating ui n plus 1. So this is one I want to calculate. And I am using ui n minus 1. This is 1. And ui plus 1n and ui minus 1. Actually, I am trying to update this point. But I am not using the past value of this point. UIN I am not using. So I am jumping, right? This is actually also called as midpoint leapfrog method. This is called as midpoint leapfrog method because it is jumping something like that from I to n minus 1 to n plus 1. N is the nth value is not using. Okay, so this has named like that midpoint leapfrog scheme. Okay, these are the difficulties. That's why, though it is a second order accurate in time and space, as I told, because the starter solution will affect the accuracy of this solution, we will lose it many times. So this is, though it is just for academic interest, we are discussing about it, but normally this is not preferred. But still, I am interested in second order in time and space. Okay, people will try, right? The later, many people have tried. So the two people again, the same lax has joined another person called Vendroff. Okay, lax Vendroff explicit scheme. Sometimes this is called as one-step scheme will come, which is two-step lax Vendroff scheme. Okay, so here this is a one-step lax Vendroff explicit scheme. So here what we do is, again, you take ut equal to minus ux at in. So if I take uin plus 1, Taylor series expansion, if I take uin plus delta t ut plus delta t whole square by factorial to utt. Okay, like this. And here we have ut is equal to minus aux and utt is equal to a square uxx. We know them. And if I substitute these two into this equation, so what will I get? uin plus 1 is equal to uin plus aux plus delta t whole square by 2 a square uxx. Okay. Now this ux and uxx, they are written in central difference form. So uin plus 1 is equal to uin plus a delta t. You can write a delta t into central difference. I write here ux ui plus 1n minus ui minus 1n by 2 delta x plus delta t whole square by 2 a square. Okay, so uxx, so ui plus 1 minus 2 ui plus ui minus 1n by delta x whole square. These are at n. Okay, if I take like this is what is called as lax Van scheme. Okay, I will write it still better way, because only
Avinash, voice interesting.
a square
Let
delta t whole square x whole square. This is c square by 2 into ui plus 1n minus 2 uin plus ui minus.
sir, there is a lag, sir.
There is a lag, no?
Yes, sir. From your side, I think.
Okay, I cannot do anything. Now is it okay?
It is okay now, sir.
Yes, sir.
So here this is the scheme. And so the order of accuracy is second order in time and second order in space. And
Sir, it's third order in time, no, sir, because we have.
Here I am neglecting from delta t whole cube like that. It is not like that. Actually, if I
Okay, we have to divide with delta t, right, throughout the equation.
yeah. Okay, so it is second order in time and second order in space. And if you take the stability, so this is also, because it is explicit scheme, c less than or equal to 1. This is condition for stability.
Sir, where are we dividing with delta t here?
No, it's not like dividing delta t. Okay, this if you do only this much, and if you do the consistency analysis, you are going to get this. Okay. Is it okay? Forget about dividing delta t in the. If I take this scheme, this particular scheme, and if I do the consistency check, so you will get the condition for stability or consistency is delta t whole square and delta t x whole square should tend to 0. Okay.
Okay, sir.
Okay, these are the explicit schemes people have come across, and then we go for implicit schemes. Okay, implicit schemes, again we go to the same like BTCS implicit, which we have used in the parabolic solver. So ut equal to minus AUX I n plus 1. Okay, backward time central space. So what will I get? The same UIN plus 1 minus UIN by delta T only I will get. On the right side, minus A, central difference, UI plus 1n minus 2 UIN plus UI minus 1n by delta x whole square.
So
But
it should
the
be
n plus 1. N plus 1, yeah. Okay. So this is order of delta T and delta x whole square, right? And stability, unconditionally stable. And so we are going to get tridiagonal matrix. So we are going to get U I minus 1 n plus 1, UI n plus 1, UI plus 1 n plus 1 are the unknowns. So we are going to solve TDMA. Okay. And so when appending differencing is working, actually people have tried that also. The second one, backward time, backward space, implicit space. So I'm going to get UI plus 1 n minus UI by delta t equal to minus A UI minus UI minus 1 by delta t n plus x. So which is the first order in time and first order in space, and stability again unconditionally stable. So here we have to solve. Here how many unknowns are there?
So left hand side, I think it should be
There is something.
left hand side we wrote wrong, sir. Time difference.
Yeah. This is sorry. Yeah, right. That's why I'm just confused. Right. UI n plus 1 minus UI n by delta t. Okay. Now how many unknowns are there?
Only one, sir.
Check it again. So this is also unknown. Two unknowns. So UI n plus 1 and UI minus 1 n plus 1 also. Two unknowns. So which, sorry, bidiagonal matrix. Okay, to be solved. Am I clear? Ui n plus 1 and ui minus 1 n plus 1. There are two unknowns will be there. Okay, anyhow, this is also not popular because it is first order in space. So usually people prefer BTCS implicit. Okay, once you discuss this, the next thing usually we come is what is called as Crank-Nicolson. So we are going to get, it is I n plus half, right? So ui n plus 1 minus ui n by delta t is equal to minus a by 2. Sorry, not like this. This is only central difference of first order derivative. Ui plus 1 minus ui minus 1n by 2 delta x plus ui plus 1 minus ui minus 1. These are n by 2 delta x. Like this. Is it clear? This is central difference, ui plus 1 minus ui minus 1. And this is implicit and this is explicit. Average of these two I will get here by 2. Okay, so this is accuracy, second order in time and second order in space, and stability, unconditionally stable. And we have to solve. How many unknowns are there?
Three, sir.
Yeah, TDN. ui minus 1 n plus 1, ui n plus 1, ui plus 1 n plus 1. Okay, so these are the things we have. Okay, these are the various schemes that we come across. Maybe, okay, we will try one of the stability thing, right? So maybe I will take upending. So what I have is forward time, backward space. So ut is equal to minus ux in. So ui n plus 1 minus ui n is equal to delta t if I take that side minus c, and backward difference ui minus ui minus 1n by delta x. Oh, sorry, by delta x is gone. Is it okay? This C delta t by delta x, I'm writing it as C.
Yes, sir.
And now if I use von Neumann stability analysis, so I have to put epsilon in all the terms and divide by epsilon in. Okay, so just I will write again. Okay, if I divide by epsilon in, what is that I am going to get here? Tell me.
E power a t.
E power a delta t minus
1.
It's 1.
is equal to minus c into
1
1
minus
minus
e power minus a delta
Minus
t.
a delta t.
minus ikmx
IKMX.
or I theta minus I theta. So this is equal to minus c into 1 minus cos theta minus I sin theta. Like this, I'm going to get. E power a delta t is equal to 1 minus c like this I will get. Am I right?
Yes, sir.
Or I can write this as 1 minus c plus c cos theta minus I c sin theta. So this is g, which is imaginary. So what I have to do is I have to take g bar. Okay, like this. This is I c sin theta. So g bar is equal to a real square plus imaginary square, right? Like this I will get. So this is equal to 1 minus c whole square plus 2c into 1 minus c cos theta
plus c square cos square theta.
c square cos square theta plus c square sin square theta. So this c square cos square theta sin square theta, it becomes c square. Okay, and here if I expand this 1
1 plus 2c.
square
Minus
plus 2c is 2c into 1 minus c cos theta plus c square. So 1 plus 2c square minus 2c plus 2 into 1 minus c.
The third term has c also. 2c into 1. Fourth term, not third term.
Yeah, for this one,
Yeah, 2c into 1 minus.
2c into, okay. Yeah. And if I come to this, 1 minus c, if I take, so 2c into c minus 1, it's common, right? If I take like this is 1 minus cos theta, right?
Right, sir.
And so this 1 minus cos theta is 2 sin square theta. So 4 sin square theta by 2 into c minus 1. It should be less than or equal to 1.
c into c minus 1.
Yeah. So here, if 1 and 1 goes off, so it will be like 4c sin square theta by 2 into c minus 1 greater than or equal to 0. So this is positive when c is greater than or equal to 1. Sorry.
C into C
less than or equal to 1, right? I think it is 1 minus.
like C also there, sir. C into C minus 1.
C into C minus 1. Okay, no problem. C is positive only. C is always positive, right? So that C minus 1 should be, it is greater than or less than?
It should be
Less than, sir. There you have written reverse. Less than or
Yeah.
equal to 0.
It should be less than or equal to 0. Actually, we will get C less than or equal to 1. This is the condition for stability. Okay, this is the way you have to prove the condition for stability. Maybe we can prove one thing which is unconditionally on. Time is there. Okay, I think time is over. We can prove some other thing like FTFS or FTCS, which are unconditionally unstable. So you can just check. So whether you will get, so there I have to get always C greater than or equal to, G bar greater than or equal to 1. So that is unconditionally unstable, like that it will come. Okay, this is the way we have to prove the stability. And so these are the various schemes. And the next class, we will talk about what is called as error analysis. So the truncation error, which is there, it has some characteristic, and what is the effect of the error on the solution. Okay, we will discuss about that. And also we will talk about multi-step methods. Okay, if you remember, I don't know whether you have studied in your numerical methods when you talked about ordinary differential equations. Okay, you might have studied about Euler method, GRKGupta second order method, fourth order method, and all. Have you discussed about multi-step methods like predictor corrector methods?
No, sir.
For us, it is being done, sir, at NSD,
Okay.
math selector.
Okay, so we will discuss about those things. They are called multi-step methods. Predictor corrector methods will be there, 2 steps. As I told, Lax-Weintraub scheme, there is a one-step Lax-Weintraub. There are 2-step Lax-Weintraub scheme also. So some of those schemes we will discuss, and we will see about the non-linearity also. Okay, those things we'll discuss in the next class. And I think for this week, the classes are over. So we will have minor exam on Monday. Okay.
Okay, sir. Parabolic solvers and hyperbolic solvers or elliptic solvers.
Whatever is covered after the first minor, those things will be there for the second minor. This is second or third? Second only, right?
Third, sir.
Third minor. Okay. Whatever is over after the second minor, for the third minor.
Including the ones in assignments.
Yeah.
Okay, sir.
Because here we are not solving any problems, right? It is only multiple choice questions.
Okay, sir.
Okay. So elliptic, parabolic, and hyperbolic, I think we all these 3, and stability also will be there. Okay. If there are any questions you can ask, otherwise we will go for the story.
Sir, Monday there might be another minor. So if there is that minor, we will let you know.
Yeah. So we can shift one day this way or that way, no
Okay,
problem.
sir.
Time also we can shift, or we can shift a day also. Okay, don't worry about that. Okay, you can just update me or inform me.
Okay, sir.
Okay, so these are the things. Actually, it is their model equation, FTPFS, FTCS, FTBS, lax explicit, midpoint leapfrog, lax Weintraub, Euler's BTCS, and implicit first upwind differencing, BTBS, and Crank-Nicholson, and this error analysis, which we are going to discuss in the next class. Okay, this will not. Okay, here we'll go for the story. I don't know whether I told this. Anyhow, there are other people also are there. There is one interesting story, lizard story. Okay, it is a true story that happened in Japan. In order to renovate a house, someone in Japan breaks open the wall. Okay, there all are wooden type walls will be there, and usually there will be 2 wooden planks or at a small distance, they will make it like a wall. Okay. And so Japanese houses normally have a hollow space between the wooden walls. So when tearing down the walls, he found that there was a lizard stuck because a nail from outside hammered onto one of its feet. So while hammering it, somehow one nail has gone into feet of a lizard and it was just stuck up there. He sees this, feels pity, and at the same time curious. As when he checked the nail, it was nailed some 5 years ago when the house was first built. What happened? The lizard has survived in such a position for 5 years. He could not believe and he didn't understand how it is surviving. So, in a dark wall partition for 5 years without moving, it is impossible and mind boggling. Then he wondered how this lizard survived for 5 years without moving a single step since its foot was nailed. So he stopped his work because how it is getting its food, how it is eating. So he stopped his work and observed the lizard, what it has been doing and what and how it has been eating. Later, not knowing from where it came, appears another lizard with food in its mouth. Ah, he was stunned and touched deeply. For the lizard that was stuck by a nail, another lizard has been feeding it for the past 5 years. Imagine, it has been doing that untiringly for 5 long years without giving up hope on its partner. Imagine what a small creature can do that a creature blessed with a brilliant mind can't. Okay, so human beings now they are not feeding the parents, they are putting in old age homes. Just you think when a small creature can do, a human beings cannot do that. Please never abandon your loved ones. Never say you are busy when they really need you. You may have the entire world at your feet, but you might be the only world to them. A moment of negligence might break the very heart which loved you against all odds. Before you say something, just remember it takes a moment to break, but an entire lifetime to make. Okay, thank you. Thank you very much. See you.
Thank you, sir.